Do you all see like the notepad right now?
Yes.
Okay, great. Okay, let's get started. Um, so today we'll go over the idea of uniform continuity. So let me just illustrate like, what that means. So if we want to show x squared, I mean, it's clear it's continuous at 0, right? Because you want to show, uh, if for all epsilon greater than 0, there exists delta greater than 0, such that, I mean, x minus 0 is less than delta, then x squared minus 0 is less than epsilon. So in this case, it's clear what delta is, right? You choose delta to be root epsilon, right? Then x squared is absolute value of x times absolute value of x, and each one's less than delta, right? And if you pick delta to be root epsilon, it's less than root epsilon times root epsilon, which is epsilon. So you get that x squared is continuous at 0. Now, it's certainly true that x squared is continuous at 1, but what happens if I choose delta to be root epsilon? Yeah? And let's say, I mean, it has to hold for all epsilon greater than 0, right? So let's say epsilon is 1. So root epsilon and epsilon is the same thing. Then in this case, you want to, it's basically saying if absolute value x minus 1 is less than 1, then absolute value x squared minus 1 is less than 1, right? And that certainly isn't true, right? I mean, if you pick, I mean, what's a number that's within 1 away from 1? Like 1.9, yeah? So it's pretty clear that that 1.9 squared minus 1 is not less than 1, right? So you see that, I mean, it's certainly true it's continuous at 1, but the same delta will not work, right? You can't choose the same delta. So basically, like for y equals x squared, the delta ball you chose around 0 will not work if you pick it around 1. So your delta in this, you see that your delta depends on like the point you choose. So basically you can ask, okay, so what about the what if I pick a delta that works at 1? Will it work elsewhere? So it turns out for x squared, like there's no one delta that works for like all points. If you consider, of course, like x squared on like all of R, right? Negative infinity to infinity. So basically, the idea of uniform continuity is your delta only depends on epsilon. It doesn't depend on where your point is. So basically, the same delta ball will work at every point. Okay, so let's write it formally, and then we'll prove formally that x squared is not uniformly continuous. Yeah. So let's write the formal definition. So f is uniformly continuous. I'll write CONT for continuous. Yeah, continuous on S if for all epsilon greater than 0, there exists delta greater than 0, such that for all xy, so this delta has to hold for every xy, and as such that x minus y is less than delta, then f of x minus f of y is less than epsilon. Yeah. So just really quickly, let me just compare it. F is just regularly continuous on S, means for all x naught in S. So here, your delta depends on epsilon and your x naught, right? There exists delta greater than 0 such that if x minus x naught. So it's really the placement of like your wording, but it changes everything. So here, then f of x minus f of x naught is less than epsilon. Yeah, so basically the idea is that the top part, you know, the same delta works for any y, right? So in the top part, if it was uniformly continuous, the same delta would work for y equals 0 and y equals 1, right? If s was, I mean, but you should think of s as like an interval, right? So, okay, so let's prove formally that, you know, that x squared is not uniformly continuous, right? So we want to show, let epsilon be greater than 0. Want to show there exists, want to show there exists delta greater than 0, such that for all xy satisfying x minus y is less than delta. I'll write it in terms of the x squared, right? So x squared minus y squared is less than delta, right? Right, sorry, epsilon. So we need to show this, right? Sadly, it's not true because what you're going to see is a typical way is choose a y. So that depends on x. So choose y equals x plus delta over 2. Yeah. So this point is certainly in this this y certainly satisfies this, right? Because if you just plug in x plus delta over 2, x minus x plus delta over 2 is delta over 2, right? And that's less than delta. But if you, so that's certainly in the delta ball. But here, if you, you know, FOIL, if you replace y, what you'll get is this is, I mean, what is this? X squared plus x delta plus delta squared over 4. So here, the x squares cancel, and I mean, the negative sign doesn't really matter because we're taking absolute value. So we get this, right? So here. Okay, so you see that this becomes an issue because I can make delta really, whatever delta I choose, I could choose x to be like super big, right? Like this bound depends on what x is. So like if you want to show f is continuous at like x, well, if I choose x to be like, you know, a really big number, this thing will get arbitrarily big, right? So you see from here, like it's not for sufficiently large x, this for sufficiently large x, the term, this thing will be bigger than epsilon, right? I mean, okay, so you see that here it depends on the point. So so let me give you an example of something where, you know, it doesn't depend on the point. So let me just be let's start off very easily first. So lines are uniformly continuous, yeah. So y equals mx plus b. So if we just consider f of x as x, it's pretty clear that you want to show for all epsilon bigger than 0, there exists delta greater than 0 such that for all xy satisfying x minus y is less than delta f of x, but f of x is x and f of y is y, right? So it's pretty clear you just choose delta as 1. I mean, sorry, delta is epsilon, sorry. Delta is epsilon. And you can try, you could try with the case where f of x is mx plus b. You'll get the same result. So I'm not sure if Neil went over this, but he said if the derivative is bounded, you're uniformly continuous, right? If you're bounded. So in this case, the derivative is clearly bounded, right? Derivative is the slope, and the slope of the line is always m, right? So it's clearly bounded. So another example, maybe a non-trivial, would be like square root of x, right? Is uniformly continuous on. So it's not if and only if. So, I mean, obviously the slope of root x is not bounded, right? Near 0, because derivative of root x is like 1 over 2 root x, and that blows up as you go to 0, right? So, but in this case, it is still uniformly continuous. So you want to show for all epsilon greater than 0, there exists delta greater than 0, such that for all x, y, satisfying x minus y is less than delta, root x minus root y is less than epsilon, right? So here's a trick. A trick is you always, again, for like continuity and uniform continuity, you always want to relate back to your delta term, right? So you always want an x minus y, right? You want to somehow go from root x minus root y to x minus y. So how do we do that? Well, okay, let's consider the square. So showing, hopefully you all agree with this. Showing this is the same as showing this, right? Hopefully you all agree. I mean, I just squared both sides. So in this case, well, what I'm going to do is I'm going to choose delta to be epsilon squared. And what you're going to see is this thing, root x minus root y squared. By definition, you're multiplying by itself, right? But triangle inequality gives me this is less than this, right? It's if I change the minus the plus. So, and here, if you have the formula, right? A minus b times a plus b is just a squared minus b squared, right? But square root of x squared is just x, and square root of y squared is just y. And we chose delta to be epsilon squared. So, right? So we just proved this statement, and then we're done. Okay. So, but there is a theorem that says So if f is continuous on AB, so this is a closed interval AB, that part's important, then f is uniformly continuous on AB. So here, so basically it's saying if we restrict x squared, like if I go back up here, if we restrict x squared to a bounded interval, then it's continuous, right? One way to see this is the derivative of x squared is 2x, right? And if you restrict to some interval, like it's gonna be, your derivative is bounded, right? But here, let's say we restrict it to restrict x squared to the interval, I don't know, 1 to 7, yeah? Then you see the proof here, right here, let me underline it. You can make it less than epsilon, right? Because what was the problem here? The problem here was I could take x large, right? I could take x large to make it bigger than epsilon. But if I'm on some closed interval, well, the biggest x can be is what, like 7, right? So So basically, if you're in a bounded interval, the take x sufficiently large doesn't hold anymore, right? So you're gonna get uniform continuity, because you could bound this by less than or equal to 7 delta plus delta squared over 4, right? And then you just choose delta so that number is less than epsilon. Yeah, and then another way is to say the derivative's bounded, right? So this is 2x, and on this interval, this thing is less than or equal to 14, right? 2 times 7. So your derivative is bounded in this case. So the ish, I mean, your derivative can still be unbounded, and it can still be uniformly continuous, but in this case, if you restrict to some bounded interval, your derivative will be bounded. Okay, so before I continue, any questions so far? Okay, so let's do one more example. So, okay, yeah, sorry, my dad's on the phone right now. Okay, so let's consider e to the x on R, yeah? So you know e to the x is certainly continuous, right? So if I put e to the x on some bounded interval, by the theorem, it's uniformly continuous, right? So let's consider it on R, right? That's R is not some closed interval. So want to show for all epsilon bigger than 0, there exists delta greater than 0, such that for all x, y, such that x minus y is less than delta, then e to the x minus e to the y is less than epsilon. Okay, so let's see this. So I need something, I need to somehow relate e to the x minus e to the y to x minus y. So how can I get some, like, at least something of the form x minus y from this? Any ideas? Okay, so let's factor out an e to the y. So this becomes what? This becomes e to the x minus y minus 1. Agree? Now, I have control over x minus y, right? So if I could choose a delta small, so x minus y is, I can make it arbitrarily small. So I can make it as close to 0 as I want, right? So e to the 0 is what? E to the 0 is 1. So I can make this, once I choose delta, I can make this however small, right? However small I want. But this thing can get however large, right? I mean, I could choose y to be, it depends on y. So like I can choose my y to be like 100,000 or something, and this thing will eventually be bigger than epsilon, right? So so no matter what, let me just write like this. Given any delta, e to the x, we can choose, so this thing, e to the x minus y minus 1 is less than or equal to e to the delta minus 1, right? Because x minus from here, right? So here, no matter what delta I choose, I just need to choose y large enough, because e to the y goes to infinity, right? Large enough, so e to the y times e to the delta minus 1's bigger than epsilon, right? So you see, this is not uniformly continuous, right? But it's certainly continuous. So an example would be like, if you want to show it e to the x is continuous at y equals 1, right? Then, then you would do this, right? It's the same game, but instead is e to the x minus e to the 1 is less than epsilon, right? I skipped some wording here, but hopefully you all know what it is. So here it's the same thing, right? I could factor out the e. So e to the x minus 1 minus 1, right? So hopefully it's all clear as x minus 1 goes to 0. E to the x minus 1 goes to 0, right? So basically choose delta greater than 0 so that if x minus 1 is less than delta, e to the x minus 1 is less than. I want epsilon over e, right? So here, so I get this, right? So once I chose that delta, this is less than e times epsilon over e, which is epsilon. But you see that the delta I chose, I mean, it depended on e, right? I mean, like from here, it's because y was 1. But in general, like here, if we take y large enough, it's just not going to hold, right? So so basically, I'm saying you're going to need a new delta for like y equals 2. So yeah, okay. Any questions so far? So the top part is showing it's not uniform continuous on all of R. Yeah. Okay. So anyways, let me continue then. So we have a notion of, a property of uniformly continuous functions. So we have if f maps u to r is uniformly continuous, and so note this is in my domain, right? Xn and u is Cauchy. So do you all know what Cauchy means? It just means the difference between the terms gets small. Then the sequence f of xn is Cauchy. Right, so this is pretty huge, right? Because you normally don't get this, right? Even for like, example, take u to be some open set, right? So take u to be, I don't know, 0 to infinity, right? Then certainly, hopefully you all remember if a sequence converges, it's Cauchy, right? So 1 over n, take xn to be 1 over n. This thing's Cauchy, right? Because, it converges, right? Because 1 over n converges to 0, right? But if we take f, so f of x is certainly, if I take f of x to be 1 over x, it's certainly continuous on 0 to infinity, right? Because, I'm taking out 0, right? So I'm not including 0. So this function's certainly continuous from 0 to infinity. But what is f of xn? This is f of 1 over n, which is what? So it's going to be n, right? And not only is it not Cauchy, it doesn't even converge, right? It goes to infinity. So here, so continuity is not enough. Yeah, so you need uniform continuity for like a sequence to be Cauchy. Okay. So any questions so far? Okay. So next thing is he made a video on like discontinuities, so I might as well go over that. So discontinuities. So for discontinuities, there are like many different ones. the first one is called removable discontinuity. Yeah, so you can think of it like x squared minus 1 over like x minus 1. Yeah. So like it's like a function that sort of has a hole at 1. Yeah, it's not defined at 1, but you could fill it in, right? So basically, because the limit exists, right? If you go x goes to 1. But you just can't plug it in, right? You have to simplify. This is x minus 1, x plus 1. So if you fill it in at 2, right? At the point 1, 2, like it becomes continuous. That's why it's called removable. It's because the graph is like at 1, and here's 2. The graph of the function is like, I don't know, it looks something like this, right? I just made it up, by the way. So the graph of the function looks something like this, right? I mean, in fact, it's a line, but it has a hole at like 1, and if you fill in the hole, then it will become continuous. So this is the nicest type of discontinuity. 2 is jump. I think this is clear. So I'm just gonna write a picture. It looks something like this, right? You go like here and then you jump up somewhere else, right? So an example would be like those step functions. So here the limit exists, but you can't just plug it in. So and then here the limit just doesn't exist. So okay, and 3, it's basically I don't know what you call it, infinite discontinuity. So this is basically like y equals 1 over x, right? It has a like f of x is 1 over x, discontinuous at 0, right? Because it blows up at 0, right? I mean, it goes off to the limit as you approach the left, and from the right blows up. It goes to it's infinite. And the fourth one is, so for those people who want to study complex analysis in the future, this is something you should know. Continuity. So here, right here, the limit didn't exist, but limit from left and from right still existed, right? So limit from the left, is like this point. Limit from the right is like this point. Here, the limit from the left and right didn't exist, but it's a set thing, right? We know it's like either infinity or negative infinity. So essential is basically limit from left or right does not exist. So the function for this, a famous one, is sine 1 over x. In fact, it's on your homework. So it looks something like this, right? It gets really wick, and then it goes like, and there's infinitely many. I should put ... here. So there's like infinitely many waves getting closer and closer, right? So here, hopefully this is the graph. F of x is, so on your homework, this is not this is not defined at 0, right? So let me just make it for homework. They defined f of 0 to be 0, right? And then f of x equals sine 1 over x for x not equal to 0. So here, right, I mean, it's pretty clear that there's infinitely many waves, right? So if you just, the reason it's not continuous at 0, I mean, if you just think about it, like there's I'm drawing finitely many, right? But if you think about it, if there's infinitely many waves, there's infinitely points where you're at the bottom. So basically, you could find a subsequence where the value is, I mean, what's the smallest value of sine? -1, right? Find a subsequence where smallest, it's tending to 0, right? It's tending to 0, right? Because it's getting closer and closer, but where the value of function is -1, or you can do 1, right? Function is -1, or you could do like 1, right? So it's gonna you're gonna need to choose something like, I don't know, like 2 over k pi, right? Something like that, where like the sequence just is tending to 0, but you remain at value 1, right? And then so you're not continuous, right? Because you need to have value 0 to be continuous. Okay, so any questions so far? Okay, so let me just quickly go over. So let me try to find it. So basically anything where, so let me just quickly, maybe give a short hint on why derivative being bounded means you're uniformly continuous. So let me just write not proved yet. Yeah, but hopefully it's something you learned in like Math 2A. So f is differentiable. So we haven't defined this either, right? So unlike a, b. So basically it's saying given any, let me just write it like this. Given any x, y in a, b, let me just put it like this. We have this bound, right? Hopefully y'all remember there exists C in AB such that f prime of C, I think it's even equal. You don't even need less than, it's equal x minus y. So hopefully you all remember this, right? I mean, it's mean value theorem. So why does this show uniform continuity? Because it's exactly set up, right? You want this guy less than epsilon, and you can choose this less than delta, right? So if your derivative is bounded, if f prime of C is bounded, then choose delta to be equal to epsilon over m, right? Because you want this to be less than epsilon, right? Let's start with this, and this is equal to this. If you like, I feel like I should put absolute value here, but yeah, let me just leave it. So it's certainly bounded by this, and it's less than or equal to m times this, and we chose our delta to be epsilon over m, right? So in fact, let me just take this off. Since I put equal sign. But yeah, see, like basically you're gonna get like it's uniformly continuous. You just choose your delta to be epsilon over whatever your derivative is bounded by. So yeah. Okay, so I normally save discussion time for homework questions, but before that, let me announce that your quiz on Wednesday, there will be a question on IVT, so intermediate value theorem. I hope you can all do that one. And then there'll be so your homework right, has a lot of questions that have you think, like give an example of something that's not bounded, that is bounded, so on and so forth. So there'll be a true false question on like continuous functions. So I'm just checking it to see if you understand the properties and definition of continuous functions. And then the third question will be prove. I'll give you a function. Give you a function. Show it is continuous or discontinuous on some set. Yeah. So yeah. So I mean that's pretty much like the main gist, right? The main gist of last week was continuous functions. So it should not be that hard. So maybe the last one, but the first two should be simple. The true false, you don't need explanation. So I just need either true or false. So again, I will upload quiz questions on files in Canvas. Questions on files on Canvas, right? At like 2:00 p.m. right, Wednesday, and then you have like 10 hours to do it. So, okay, any questions? So nothing on uniform continuity for the quiz. Okay, if not, I'll just stay here if you have homework questions. If not, you're free to go. Word.